Our last video on this section about the ideal gas law is just an example calculation. This is an example exercise from the textbook, but I thought we could work through it together. So I thought this was a nice application of the ideal gas law. And again, this is going to be under conditions where this works quite well, and so the values you get from this are going to be pretty close to what you would actually observe in real life. And so what we're imagining is that we start with a weather balloon that has 100 liters. In the problem it says that this is helium. It actually doesn't matter which gas it is, as long as it's one that behaves like an ideal gas. So it could be nitrogen, it could be oxygen, but helium is going to float better. So the other ones won't float. So that's why you would use helium for something like this, because the weight is lower and it's buoyant. Anyway, volume is equal to 100 liters at the ground level, where the temperature is 20 degrees Celsius and the pressure is 755 torr. Now, that weather balloon goes up into the air with its instruments, measuring, pressure and wind speed and temperature and whatever up in the upper atmosphere. And it gets up to an altitude of 10 kilometers. Up there, it's much colder. It's about negative 52 degrees Celsius, and the pressure decreases drastically. There's a lot less gas pushing on you up there because you've gotten above most of it. And so the pressure is about 195 torr. And the question is, using the ideal gas law, what is the volume once it reaches that altitude of 10 kilometers and reaches these conditions? So let's go ahead and go through this. There's a couple ways of approaching this, but what I immediately look at is we know pressure, we know temperature, we know volume, and the initial. There's one thing that we don't know, which is how many moles did we start with? And that's not going to change. As the balloon goes up, it's not presumably leaking any helium into the atmosphere around it, and so the number of moles will stay constant as we go. And that will leave us one unknown in our second, right? Once we know N, then only V will be our unknown, and we can use the ideal gas law there. Okay, so let's go ahead and calculate the number of moles. There are other ways of doing this where you sort of cancel things out, but this is the way that makes most intuitive sense to me. So we'll work through it this way. Your textbook uses a slightly different approach, but you get the same answer either way. All right, so first things first, whenever we're dealing with things with the ideal gas law, we need to convert all the temperatures to Kelvin. So our 20 degrees Celsius, again, to convert to Kelvin, we add 273. So that gives us 293 Kelvin. All right. Now, why do we add 273? It's because absolute zero is negative 273 degrees Celsius. So to get it into Kelvin, we add 273 to Celsius. And then negative 52 degrees Celsius, we add 273. That one I can't do in my head so easily because it's not just adding 20. Where's my calculator? So we're going to have 273 minus 52, which gives us a temperature of 221 Kelvin. Okay, great. Now, let's go ahead and find the number of moles for our balloon before it takes off, which again is going to be the same number of moles after it's gone up into the atmosphere. So we can take the ideal gas law, PV equals nRT, and rearrange this so N is on one side and everything else is on the other. So we can do that by dividing by RT. So we'll get N is equal to PV over RT. And then we can plug in all the values that we know. Again, we'll need to choose the value of the ideal gas constant to match the units that we use for everything else here. All right, so that's always a key part of the ideal gas law. There's several different values of R that you can use in your textbook. It's table 5.3. There's a few different values. So for this one, since we have the pressures in torr, we're actually going to use R in liters times torr, because that's the volume is in liters, our pressure is in torr, divided by moles times Kelvin. And from your textbook, that is equal to 62.37. So that's not something you need to memorize, but that is the value of R we're going to use in this problem. Again, that's completely the same as the other values of R that we discussed, just the units have changed. So R is the same value, just the numerical value changes because we're expressing it in different units. Okay, let me give myself a little bit more space here. We can plug in all of our values. So P was equal to 755 torr. V was 100 liters. R is the value we have up here, 62.37 liters times torr over moles times Kelvin. And then our temperature was 20 degrees Celsius, which is 293 Kelvin. Okay, so let's go ahead and plug that into our calculator, and we can figure out how many moles of gas was this. Again, helium is what was used, but this would work for any gas, because as long as it behaves ideally. So 755 times 100 divided by 62.37 with the parentheses there times 293 gives us 4.13 moles. I'm going to add an extra digit just so we don't lose 4.1314 moles of gas. Okay, so now we can use that value. That N is not going to change. The balloon isn't leaking, right? So if we go back up here, we know our temperature and pressure and our number of moles now, and so we can find volume. So similar to what we did below, we can take PV equals nRT and rearrange to solve for V. So if we divide by P on both sides, we get that V is equal to nRT over P, and now we'll just plug in all these new values that we have. All right, so we're going to use the same value of R because we're going to use torr in liters again. So we have, again, our number of moles was 4.1314. Okay, make sure I get the right value. 4.1314 moles, 62.37 liters times torr divided by moles times Kelvin. Our new temperature is 221 Kelvin over here in the corner. I'm going to move over so I actually have space to write it though. And our pressure, oops, don't want to cross that out. Our pressure is, coming back over, 195 torr. All right, so what we should get is our moles cancel, our Kelvin cancel, and our torr cancel. So this should give us liters, and we can go ahead and plug these values in. Find my calculator again. So our same value, I can just copy that, times 62.37 times 221 divided by 195 gives us a volume of 292 liters, which matches what the textbook says, which is always great to agree. All right, so the balloon gets almost 3 times as big in terms of its volume. Kind of interesting, huh? And that actually happens anytime you launch a weather balloon. As it goes up, the volume of the balloon is going to get bigger and bigger. So you have to use a material that can withstand that change in volume. And it mentions actually in the practice exercise afterwards that the balloon gets so big eventually that it bursts intentionally so that the instruments that it uses to record the weather actually come back down to Earth so you can get the data off of them and things like that. So that's an example of how we can use the ideal gas law and do calculations. Again, some things to watch out for when you're doing these calculations are to make sure you're expressing your temperatures in Kelvin. So you're probably going to be given temperatures in degrees Celsius. Make sure to convert those to Kelvin, and make sure to use the value of R that matches the units that you're going to be using in the question. So in this case, we use the 62.37 because we use liters times torr. But if you're looking at atmospheres instead of torr, it's a different value for R, different numerical value. So those are a couple things to keep track of. And then also as you're going from, say, 2 different things, go from one state of the gas to another state of the gas, keep track of what's staying the same. In this case, it was the number of moles stays the same because the balloon doesn't leak. So anyway, we'll see you in class, and we'll talk about this and do some more practice problems together.